Good morning, ladies and gentlemen. Let's go ahead and share our responses when I call on you. So given a picture, we can evaluate function values and limits, right, graphically, simply by using our knowledge of what it means to be a limit. And so first of all, some function values. F of 0, go ahead and share with the class. Grace? 2. Raise your hand if you have the same as Grace. 2, thanks. F of 1, Sydney?
1.
Is 1, nice job. Raise your hand if you have 1 for the second one. Good. F of 2. Actually seems similar. F of 2, Kobe?
Negative.
Negative 2, nice job. Negative 2. F of 3, Courtney? 2. 2. Awesome, thank you. And now let's switch gears. And so let's switch from our function evaluations to our limit evaluations and see how that's similar versus how it's different. So the limit of f as x goes to 0. What did you get for that one? Danny?
Does not exist.
Does not exist, and why did you say does not exist?
Because the left-hand limit doesn't go to the right-hand limit.
Good, and so here we've got the left-hand limit, the y values are approaching, y equals 0. The right-hand limit, the y values are approaching, y equals 2. Since those y values are not the same from the left and from the right, the overall limit does not exist, D and E. Nice job. Raise your hand if it does not exist for that one. Good. The limit of f as x goes to 1. What did you have for that? Tyler?
1.
1. The left-hand limit matches the right-hand limit, and both are the y value 1, therefore the value of the limit is 1. Raise your hand if you have 1 for the limit of f as x goes to 1. Do you have 1? That's great. So we see when our left-hand limit matches the right-hand limit, matches the match each other, then we've got the overall limit existing. Let's take a look at the limit of f as x approaches 3. What'd you get for that one? Riley?
2.
2. Raise your hand if you had 2 for that one. 2 for that one. Great. Thanks, hands down. And lastly, the limit of f as x approaches 4. Right? What did you get for that one? Danny?
4.
4. So what's going on here? Raise your hand if you have the same as Danny. Did you get 4? You get 4. Good. So the function need not be defined at x equals 4. In order for the limit to exist, we just need the left hand to match the right hand, and that should be old news. So everybody good to go? That's old news. Now let's go ahead and build on it today with our Hopital discussion. But first, let's get you credit for your OTL number 5. I'll pause the recording. Please make sure that you have your name. Okay, ladies and gentlemen. So let's go ahead and take a look at the eternal question, right? Is this initial evaluation generate a determinate or an indeterminate form? And we saw last time when we were evaluating limits algebraically that if we got a 0 over 0, right? If we got a 0 over 0, then that was what we call an indeterminate form, right? An indeterminate form. While that's undefined, right? While that's undefined, oftentimes the value of the limit did exist, and we had what we saw in the last problem of our Bellwork, where there was maybe an open circle, where the value of the function did not exist, right? And yet, the value of the limit did exist because it was smooth, the left-hand limit matched the value of the right-hand limit, so the overall limit existed. So 0 over 0 is what we call an indeterminate form, and that should be ATE. Let's go ahead and consider other quotients, like infinity over infinity. And so if we had infinity over infinity, where did I clone from? This is another indeterminate form, right? Infinity over infinity is another indeterminate form. We can't tell what the value of the limit is or isn't simply by looking at the expression, and so we've got some more work to do. Up until now, we've got lots of algebraic tools. In fact, we remind you about some of those last time. We had factoring, we had multiplying top by the conjugate, we had find a common denominator, right? So we had all kinds of algebraic ways that we could handle it. What I wanted to do is to consider some other quotients, right? Like what if we had a constant on bottom and a quantity approaching 0 on top? Is this indeterminate? No, if we have a constant on bottom and a quantity approaching 0 on top, this is determinate, right? That's approaching 0. So there's no problem there. Similarly, if we have a constant over a quantity approaching 0, right? Is this indeterminate or determinate? This is determinate. If my top is fixed and my quantity on bottom is approaching 0, this is ballooning to one of the infinities. And how do I determine which? Well, I consider a sign test, right? What's the overall sign of the quotient? I'll consider if the top's positive or negative, the bottom positive or negative, and then overall positive or negative. So what I'm going to do is I'm just going to write this is equal to plus or minus infinity. This is equal to 0. So these are both determinate, right? They're both determinate. We can tell exactly what the values are just by looking. All right. Similarly, if we had the infinities, right? If we had 0 over a quantity becoming infinite, constant over a quantity becoming infinite, in each case, right? These are going to 0. They're all determinate. And if we had infinity over a constant, there's nothing indeterminate about that, right? This would be going to positive or negative infinity as well. So all of these are going to be on the determinant page for our PDF, come on, baby. So all of these are going to be on our determinant page. So once again, our indeterminate quotients, those that we can't tell the value of the limit simply by looking at the expression, include 0 over 0 and infinity over infinity. And this could be plus or minus, right? It could be plus or minus, but those are our indeterminate quotients versus our determinate quotients. If you generate this in your initial evaluation, or even after you've done some work to rearrange, if you generate one of these determinate forms, stop. Put the answer as being 0 or infinity or one of these, okay? All right, now let's go ahead and consider what happens. My clones didn't clone. Let's go ahead and consider what happens if we consider sums versus differences. And so if we have a quantity that's approaching infinity, plus another quantity approaching infinity, I want you to consider if that's determinate or indeterminate. Well, there's nothing indeterminate about an infinite quantity plus another infinite quantity is going to be an infinite quantity. So this is certainly determinate, and that would be going towards infinity. Where we run into a sticky situation is a difference, right? An infinite quantity minus an infinite quantity does not equal 0. I want to be nice, but remember, infinity is not a number, it's a description, right? It's a description of a quantity that's getting infinitely large. And as we've seen in the past, we have quantities that grow at a different rate. If this first quantity is growing at a much quicker rate than the second quantity, right, it's going to win the tug-of-war struggle and pull the overall value of this to infinity. Right? This first infinity will win, and the second infinity will be negligible or small compared to the first, then overall this will be going to infinity. Contrast that with my second quantity growing more quickly. If my second quantity is growing more quickly, then it's going to win the tug-of-war battle, and it's going to pull this value down towards negative infinity. Or is there some balancing point, some break-even point, where their relative rates of growth, right, balance one another out, and we approach a constant? Right? Could it be that we're approaching some constant, call it k? And that often is the case with these indeterminate forms as well. That's why this is indeterminate. And so an indeterminate difference exists if we get infinity minus infinity. A similar argument can be made for products. If we had 0 times infinity, remember we're talking about a quantity approaching 0 times the quantity approaching infinity. If the first quantity approaching 0 wins out in my relative rate of growth, right, then it's going to pull the overall value of this quotient towards 0. However, if the second quantity, that infinite quantity, wins out and grows more quickly than the first one shrinks, it's going to pull the overall value of this towards infinity. Or again, is there some balancing break-even point? And so that's why we have the indeterminate product 0 times infinity. There's nothing indeterminate about the other combinations, right? 1 times infinity, if we're multiplying, right, that'll become infinite. 1 times 0, if we're multiplying, that'll go to 0, right? And so the indeterminate product will just cut right to the chase of the 0 times infinity, plus or minus either order. All right, that brings us to powers. So our powers discussion was the trickiest of all last year, and we didn't spend much time with it. In BC, we're going to investigate them in a little bit more detail. And so consider our powers. If we did something like 0 to the infinity, right, 0 to the infinity, we're talking about a quantity that's approaching 0 being multiplied by itself over and over and over again. Is this determinate or indeterminate? Well, there's nothing indeterminate about this. This would be going to 0. That is determinate. So this would be going to 0, no problem. Similarly, if we add 0 to the first, right? 0 to the first, this is no problem as well. This is determinate. This is approaching 0. Anything raised to the first power is itself. And so this is also approaching 0. Where we run into gray areas is when we have things like this. 0 to the infinity. Right? 0 to the infinity. Is no problem. Because we just did 0 to the infinity. How about infinity to the 0? There we go. How about infinity to 0? I don't have time to make my corners. They were excited about that. I already did 0 to infinity. Infinity to the 0, right? What's wrong with this? Well, recall our definition of 0 exponents, right? 0 exponents arose from taking x to the 7th over x to the 7th, right? That's x to the 7 minus 7 is x to the 0. Infinity to the 0 would be like infinity over infinity, and this gets us right back to our indeterminate quotient. And so infinity to the 0 is indeterminate. If, right, we consider values here, when our exponent's approaching 0, that's trying to bring the overall value towards 1. The base, however, is approaching infinity. As I multiply that over and over again, right, then we're thinking, oh, is that going to be infinite? And that's why this is indeterminate. Here's a stickler. What about 1 to the infinity? Last year we saw how the quantity approaching 1 makes all the difference. If that quantity approaching 1 is a little bit less than 1, like 0.9, repeated multiplication by itself is going to shrink towards 0. 0.9 times 0.9 is 0.8, 1. Times 0.9 again is 0.729, and it's shrinking, it's shrinking, it's shrinking. And so this is also indeterminate. And lastly, our 0 to the 0. The base is trying to bring the value of this towards 0. The exponent is trying to bring the value of this towards 1. Who wins? We don't know. It's indeterminate. Also, we could think about this definition of 0 exponents was 0 over 0, right? Dividing itself, and that is one of our indeterminate quotients from here. So our indeterminate forms are 0 to the 0, infinity to the 0, and 1 to the infinity. And my clone worked on this one, so that's good. All right, so we've got that, and I can do one page. All right, so in summary, we've got our indeterminate forms. Let's go ahead and make them all in one place. So on your note sheet, everybody have your note sheet? So our indeterminate quotients, what's one indeterminate quotient? Sophia?
Infinity over infinity.
Infinity over infinity plus or minus, good. And the other indeterminate quotient, Riley?
0 over 0.
0 over 0, awesome. Our indeterminate products, well, there's just one product, and it is 0 times infinity. So 0 times infinity is our indeterminate product. We've got a single indeterminate difference, that's the infinity minus infinity. And our indeterminate powers include our 1 to the infinity, our 0 to the 0, and our infinity to the 0. All right. So these are the various indeterminate forms. Today we're going to see how we can work through these indeterminate forms and get values from any of these limits. Sometimes we won't be able to, and sometimes we will. What allows us to do this is, oftentimes, L'Hopital's rule. And so if the evaluation of my initial limit of a quotient, f of x over g of x, as x approaches a constant or as x approaches infinity, results in an indeterminate quotient, that is 0 over 0 or infinity over infinity, then L'Hopital's rule authorizes us to take the derivative of the top, the derivative of the bottom separately, and try again. And so what we're going to do is take the derivative of the top and the derivative of the bottom, and then try to evaluate the limit again. Right? So this is a new algebraic tool to go along with our factoring, multiply, top, bottom by the conjugate, least common denominator, etc. Let's go ahead and see how we can apply it. So let's find each limit algebraically if it exists. Please note, we're still going to do an initial substitution. Right? We always want to try direct substitution to evaluate right off the go and see what we're working with. So as I let x go to 0, e to the 2 times 0 is 0. E to the 0 goes to 1. Minus 1 is 0 over x is going to 0, so I'm getting 0 to 0, right? This is an indeterminate form. I can't tell what the value of this limit is or isn't simply by looking at it. However, my original tools like factoring, right? Though I can factor the top. I can factor the top. That's actually a difference, right? That's a difference in perfect squares. I could factor the top, but will it do me any good? The denominator is just x. I won't be able to cancel out any factors, and so it's not going to do me any good. This is one where we have to apply L'Hopital's rule to evaluate. No problem. L'Hopital's rule is awesome and easy. It says that the initial evaluation results in an indeterminate form, 0 over 0, or infinity, check. Then we're authorized to utilize L'Hopital's rule, where I'll simply take the derivative of the top, the derivative of the bottom separately, and then try again. For us, we want to make sure that we're keeping the limit expression. We're differentiating the top and bottom separately. We're not applying the quotient rule. So don't apply the quotient rule. We're differentiating top and bottom separately. So e to the 2x goes to 2e to the 2x minus derivative of 1 is 0 all over 1. And I get 2e to the 2x. As x goes to 0, e to the 0 is 1 times the 2 out front. Equals, gosh, I'm getting 2. We're getting 2? All right, just so I can get some more hours involved. 2. Agreed to start with honest. All right, why do I have the emulator here? I know, because I wanted to check. So we're not going to do this for everyone in the interest of time, but I want to go ahead and check here. So I'm going to go to my original, and we want e to the 2x. Minus 1 divided by x. Yes? All right, and we're letting x go to 0, so I'm going to zoom 6. And if I zoom 2, enter, just so I can get a nicer picture. Look, because I want to. Are there any problems here? Well, if I trace, I want to trace 0, enter, just to show that, yes, the function's undefined at x equals 0, and yet the left-hand limit matches the right-hand limit, and it sure looks to me like it's approaching the y value of 2 from either side. So what we've done is we've seen graphically then, right, how our algebraic generation was correct. Hey, that's going to be sweet for the PDF. You guys see that? It's pretty nice. I mean, not that that's what I'm all about, it's just big part. All right, let's go ahead and take a look at some others, and we're not going to be able to check every time with the emulator in the interest of time. The initial evaluation of my limit through direct substitution is trickier when my x value, right, isn't c, but infinity. So that's not a particular x value, and yet we can still consider what e to the negative x is doing. E to the negative x as x goes to infinity is like, right, is like e to the negative infinity, or 1 over e to the infinity. Overall, that's shrinking towards 0. The right-hand product, the right-hand factor in my product, square root of x, as x goes to infinity, goes to infinity. And so I'm dealing with 0 times infinity. Is this determinate or indeterminate? Well, we look at our checklist, right? Is this one of my determinate or indeterminate forms? Marissa?
Indeterminate.
Indeterminate, right? And yet, does it authorize the use of L'Hopital's? No, I'm not authorized to use L'Hopital's unless I have 0 over 0 or infinity over infinity. And so we cannot use L'Hopital's rule unless we have an indeterminate quotient. No problem. We've got some tricks to rewrite products as quotients. For example, that e to the negative x, definition of negative exponents is fractional, right? Negative exponents don't mean negative answer. They mean reciprocal, 1 over, 1 over. And so I'm going to go ahead and rewrite this original, not L'Hopital's rule. I'm not putting any little h there for the hospital. I'm just going to go ahead and rewrite my original product algebraically as a quotient. That is to say, e to the negative x is the same as 1 over e to the positive. Now let's go ahead and try again. As x goes to infinity, the top goes to infinity. The bottom goes to, where's the bottom go to? Infinity. Hey! We've generated an indeterminate form that does authorize the use of L'Hopital's rule. That is a quotient. So let's go ahead and do L'Hopital's rule. The limit as x goes to infinity of, and L'Hopital's rule says we differentiate top and bottom separately and try again. So here we go. The derivative of the top, the square root of x is 1 over 2 root x. Over the derivative of the bottom, e to the x is e to the x. I don't know what this is, so I'm not doing any L'Hopital's rule. I'm just going to rewrite this complex fraction as a single fraction. By kicking that down on the bottom, I get 2 root x, e to the x on the bottom. And now it's easy to see. As x goes to infinity, I get 1 over 2 times infinity is infinity. I'm getting a determinate or indeterminate form. Determinate. I've got constant over infinity. What's this limit going towards? 0. Now we totally look at the emulator, right, and verify that using tables by choosing larger and larger values of x. We had more time, but we don't, so we won't. So let's keep on keeping on. So we've seen indeterminate product. Let's take a look at this bad boy. Good thing we remember what our trig functions look like. I know that secant of x, right, kind of looks like my parabolas, right, with vertical asymptotes. As x goes to pi over 2 from the left-hand side, that's like 1 over cosine of x. As x goes to pi over 2, cosine of x is going towards 0. So I'm getting 1 over 0 is an infinite form. So I'm getting infinite for the secant x minus, similarly, I've got my little cubic-looking swoops for tangent, right? With asymptotes whenever the denominator of tangent, sine over cosine is 0, which happens to occur at the same places as secant, right? Both have the denominator of cosine when rewritten in fractional form. Therefore, as cosine of my angle gets closer and closer to, let's see, pi over 2, I'm getting another infinity. So I'm getting infinite minus infinite. Is this determinate or indeterminate? Well, this is indeterminate, right? Based on relative growth rates, one of these infinities, right, could win the tug-of-war battle, and we don't know which. So what are we going to do? Well, we're going to try to rewrite this as an indeterminate form that authorizes the use of L'Hopital's rule, and that's a quotient. So how in the world would I make a difference into a quotient? What do you guys think? Rewrite the trig functions. So we could write secant of x as 1 over cosine of x. I want Danny on my team. Let's try that. So we're going to rewrite secant of x as 1 over cosine of x minus, and then we're going to write tangent of x as sine of x over cosine of x. And when I write my quotient identities, I'm trying to introduce quotients because those are the indeterminate forms that authorize the use of L'Hopital. In rewriting this, I see now that I have a common denominator, and I could rewrite this as a, not a difference, but as a fraction if I combine these. So I'm going to go ahead and do the limit as x approaches pi over 2 from the left of 1 minus sine of x all over cosine of x. Yes? Try again. As x goes to pi over 2, sine of pi over 2 is too tough to tame? You have a circle quiz instead here? 1. 1 minus 1 is 0. Over cosine of pi over 2 is 0. Guys, this is a big win. Why? Well, because now I have a form, an indeterminate form that does authorize the use of L'Hopital. So here I go with my check mark, and I'm ready to do my little L'Hopital's rule application, which says keep the limit expression, but differentiate the top, differentiate the bottom separately, and try again. So I'm going to differentiate the top. Derivative of 1 is 0, minus the derivative of sine of x is cosine of x. So I still get negative cosine x on top. Sine differentiates to cosine, but I had the negative built in already. The derivative of cosine of x is Opposite sign of x. So I've differentiated, and now I'm going to try again. So as x goes to pi over 2, what does cosine of x do? 0. Over, as x goes to pi over 2, what does sine of x do? Goes to 1, so I'm getting negative, then I'm getting, so I'm getting negative 1. Are you guys getting that? Is this indeterminate? No. This is determinate, and it equals what? 0. So they're awesome. 0, 0. 0, 0. Sorry, 0. Cool? Yes! Gosh darn it. That's pretty sweet. All right, let's go ahead and try another. As x goes to 0 from the right, my first term goes to 0. My second term, I've got to visualize now. Natural log of x, what does that do? Well, as x goes to 0 from the right, math woman shoots down towards negative infinity. Yes, my natural log function. So I've got 0 times negative infinity. Now we wrote our indeterminate product as 0 times infinity, but that counts for plus or minus infinity. So this is an indeterminate product. However, only quotients that are indeterminate authorize the Hopital's rule. So what do? Well, I figure right about 9 o'clock is kind of our limit for wantable field trip, and so if we can stall this out another 10, I think we're good to go. We can call it a day. Yes? Yes? No, we got lots more to do, and so I'm going to rewrite this as a quotient so that I can evaluate this algebraically, hopefully generating an indeterminate form that authorizes the use of Hopital. So let's go ahead and hang tight. Here we go. Danny recommended rewriting our trig functions using our quotient identities to introduce a quotient so I could get 0 over 0 infinity or infinity. I don't have any trig identities to apply here. I've got natural log. So what else are we going to do? How else could we generate a quotient in this expression? You going to come back to it, Tyler?
Can we change it to x squared ln of x over x?
X squared ln of x over x. Oh, would make a quotient. Yes, that would make a quotient. Then I would get 0 over. Oh, I like that. That's a good idea. I don't know if it'll work on it. We can try it. Multiply top amount by x.
Yeah.
And that introduces a quotient. I like that idea. I was thinking of rewriting a product as a quotient using multiplicative inverse. In order to multiply fractions, you flip and multiply. So I was just going to rewrite this x as 1 over x. See what I'm saying? But I like that idea too. Kind of want to try it. You want to try it? Let's try it.
No.
I don't know if this is going to work or not. We'll see. It's going to make a more complicated rule, I know that. So we're going to do a tester because I don't want to stifle Tyler's creativity. So we're going to make this x squared ln x over. Oh, I know why we're not going to do it this way. Because we still have the indeterminate quotient on top that we can't say it goes to 0 or not. Like, yes, this is going to 0, and this is going to 0, and that's 0 over 0, and I'm happy, but this is still going to negative infinity, and so I have 0 times negative infinity, which is still indeterminate, so I can't say that that goes to 0 overall or infinity overall. And so that's why we're not going to do that. Good idea, though. I like it. All right, so that's okay. We're just going to write this x as 1 over x, right? 1 over the reciprocal. So let's go ahead and keep this as the limit as x approaches 0 from the right of, but we're going to rewrite x as 1 over x, the reciprocal on the bottom. Dividing by 1 over x is the same as multiplying by x over 1, and I get my original. So do you see how we did that previous style? So we just rewrote this as that x or the 1 over x on the bottom. Why is that helpful? Well, now what happens? As x goes to 0 from the right, ln of x goes to negative infinity still, over, as x goes to 0 from the right, 1 over 0 is going to, that's an infinite form, right? A constant over 0 is an infinite form. Guess what, you guys? We get to do the check. we have a indeterminate quotient that authorizes use of Hopital's rule, so now we can go ahead and go to the hospital. So I'll go ahead and do the limit as x goes to 0 from the right. What does Hopital's rule say? It says we can differentiate the top, differentiate the bottom separately, and try again. So I keep my limit expression. The derivative of the top, ln of x is 1 over x. The derivative of the bottom, 1 over x is opposite of 1 over x squared. Mr. Fritz, how do you do this so quickly? Because come on, it's BC time now, and we've done lots and lots of derivatives, comma baby. I'm going to rewrite this one more time before I try my subsequent evaluation, because I don't like the complex fraction. I think it's going to be easier to see what the value of this is or isn't if I rewrite it. So I'm going to go ahead and rewrite this as a single fraction. I'm getting negative. I'm getting x squared over x. So I flip and multiply. Flip and multiply. Come on, guys. And that means I'm just getting, what is that? Negative x. Are you guys getting negative x? And as x goes to 0 from the right, as x goes to 0 from the right, what does negative x do? Goes to negative 0. That's not indeterminate. That equals 0. Awesome. Okay, before we go further, I just want to go ahead and make sure that we're adding our tools to our algebraic bag. So what do we have? Well, last class we had our regular algebraic tools from AB, like factoring, right? Least common denominator creation, multiplying top and bottom by the conjugate. Now, we're trying to make things look like a quotient. So what can we do to that? We did trig identities to create a fraction. We did multiply by the reciprocal, right? Or rewriting, I guess, a product as using the divided by the reciprocal, right? So we've got that as a way to make a quotient as well, because only the quotients authorize these to be taught. So what else do we have? Well, we've taken care of our products, we've taken care of our quotients, and our differences as well. What happens when we run into a power? So let's see initial substitution as x goes to 0. 4x goes to 0, sine of 0 is 0, so I'm giving 1 to the cotangent is cosine over sine. As x goes to 0, right, cosine goes to 1, and sine goes to 0. I'm getting 1 over 0. 1 over 0, is that indeterminate? No, it's infinite, and so I'm getting 1 to the infinity, right? What's wrong with 1 to the infinity? It's indeterminate. I can't tell what the value of that limit is or isn't simply by looking at the expression. So we need to figure out a way to evaluate this algebraic. So what tools do we have? Well, our trig identities, right? Though we have trig functions, aren't going to help us create a quotient here. Overall, we need 0 over 0 or infinity over infinity. So we're going to tap into something else, and that will allow us to rewrite this exponential expression. So what undoes exponents? Logarithms. What we're going to do is we're going to call this y. And we're going to take the natural log of both sides. After application of the function interchange theorem, which works for continuous functions, we're going to go ahead and bring down that exponent in front as a multiplier, create a product, and then hopefully create a quotient. And so it just adds another layer. Keep in mind that we're figuring out what the value of ln of y is going to equal. And so at the very end, we still need to exponentiate, that is, undo my natural log by doing e to the in order to get my final answer. So this is another layer. I'll take the natural log of both sides, and then utilize my function interchange theorem for continuous functions. It allows me to scooch that limit, right, and switch it with the natural log, so long as my function is continuous from the right as x approaches 0, and it is. So I'll go ahead and do natural log of y equals the limit as x goes to 0 from the right of the natural log of 1 plus sine of 4x all to the cotangent of x. So at this stage, you might be thinking, this doesn't look simpler at all. In fact, it looks more complicated, not less. To which I would reply, yes, it does. However, because we have the log, right, of a power, we can now bring down that exponent in front as a multiplier. And that's where we're going to be able to make this look easier. So I'm still keeping all this business but I'm bringing down my cotangent of x as a multiplier. Now let's go ahead and try. As x goes to 0, we've already seen that cotangent of x, that's cosine over sine, is going to infinity. As x goes to 0 from the right, we've seen that sine of 0 is 0, plus 1 is 1, natural log of 1 is? Is this determinate or indeterminate? Indeterminate. We wrote it 0 times infinity, but infinity times 0, it's a product, so, or it doesn't matter, so this is indeterminate. Does it authorize the use of L'Hopital's?
No.
What are we going to do? Well, we need to make this look like a quotient. So now what can we do to make this look like a quotient so that we could generate an indeterminate form?
1 over cotangent. 1 over cotangent.
Yes. Or cotangent is already a quotient. If we write it as a quotient, cosine over sine.
Just trying to make it more difficult.
Yes, and. Yes, and. So how about that? Yes. It's BC, guys. We can handle this. Look at that. We can handle this. Okay. As x goes to 0 for the right-hand side, cosine of x goes to as x goes to 0 from the right-hand side, sine of 0 is 0, 1, ln of 1 is
0.
as x goes to 0, sine of x goes to 0. Guess what, guys? Indeterminate form 0, 0. Quotient authorizes the use of L'Hopital's. Finally, what does L'Hopital's rule say? It says differentiate the top, differentiate the bottom separately, try again. So now we finally able to apply L'Hopital's rule. I'll signify that with a little h. That is not an AP College Board thing. It's Mr. Fritz's little thing to say, hey, this is where we're doing L'Hopital's rule. This is where we're applying it and taking the derivative to the top. What rule do we have to apply for the numerator? Product rule, because I have two separate functions of x, right, occurring. I have to use the product rule. So the derivative of a product of functions is the derivative of the first, cosine goes to opposite of sine, times the second. Plus the first times the derivative of the second. The derivative of the natural log is 1 over the function times the derivative of the function. You signed up for this one, I don't know. Yeah, this is crazy. Top, derivative of 1 plus sine 4x is 4 cosine 4x. You guys are awesome. Holy guacamole. All over.
Sine squared.
The derivative.
No.
We're not doing the quotient. We're not doing the quotient. We're doing the derivative of the top, product rule, over the derivative of the bottom separately. This is we're trying to be easy now, right? What's the derivative of sine of x? Okay. So you might be thinking, right? Look at that numerator. But guys, I know, right? I know that we're going to be done here. Because cosine of x, as x goes to 0, goes to 1. Where's my limit? I need my limit. Oh, I was worried about space. I am still worried about space. Maybe we can go like this. Group it, and then let's go like this. Just enough to get our limit in there. Okay, ready? Let's try it. Here we go. So what was all that good for? Well, now as x goes to 0, this first thing, right, goes to 0. As x goes to 0, this goes to 1 times 4 over 0 plus 1 is 1. All over, as x goes to 0, cosine of x goes to... Is this indeterminate? No! This is 0 plus 1 times 4 over 1. This is determinate and it's a constant. What do we get?
4.
4. Right, we get 4. But what equals 4?
Natural log of
The natural log of y equals 4. Is the value of my original limit 4? No. the value of my original limit, right, is only gained after I exponentiate. To rewrite my original expression, my original limit is what I called y, so we need to go ahead and do e to the, in order to get my final answer. This is a log base e, so e to the fourth equals y. So my original limit, which I called y, is e to the fourth. How about that? So, we've been tiptoeing around how the BC curriculum involves all the stuff in AB, and so we've got to review all the AB stuff. And now, finally, let's take it to the next level. Let's do some BC stuff. Okay, that was pretty good. Awesome. So, we've now handled, guys, you're doing well. We've now handled indeterminate products, indeterminate differences, right? And now indeterminate powers. What's our tool? We'll go ahead and call the original y and take the natural log of both sides. Proceed as we did earlier, but then you have to remember to exponentiate at the end. Let's try another. Go ahead and do this with your partner. Be ready to share your answer. Oh, do I give you one that's me. I got right to the one where, okay, sorry. Never mind. As x goes to pi, what does sine of x do? What's a 0? As x goes to pi, what does cosine of x do?
-1.
-1. And so I'm getting 1 minus a -1. I know I put this right about in the middle. Is this indeterminate?
No.
No, there's nothing indeterminate about this. This is 0 over 2, a constant, and so the overall value of this is 0. And so I put this in the middle because, hey, only start differentiating and applying Hopital's rule, right, when authorized to. There's no reason here to start differentiating and vary cosine. You see what I'm saying? This is 0. Period. Good? Awesome. All right. So you want to try this now? This is what you're trying with your partner, and I'm pausing the recording. This is what you're trying with your partner. Okay, and so how did it go working with your partners? On that, is that okay? So we had a double application of L'Hopital's rule. In order to use L'Hopital's rule, we had to have an indeterminate quotient of the form plus or minus infinity over infinity or 0 to 0. I got the double check mark to show that. In between, we did some algebraic simplifying and rewrites to make sure we knew what we were working with, to see if we had a determinate versus indeterminate form along the way. And our final result there, of my original limit was 1. So that's pretty sweet. All right, a couple more to close out the day and remind us about our different algebraic techniques, and then you'll have an opportunity to start your OTL, which is what I was working for. Let's get started. As x goes to 1, what happens? 1 from the right, natural log of 1 is what? Oh, natural log of 1 is 0, right? ln of 1 is 0, and so I'm getting 1 over 0. 1 over 0 is an infinite form. Minus, as x goes to 1, 1 minus 1 is 0. I'm getting an infinite form minus an infinite form. Hey, that reminds me of our indeterminate difference. So this is indeterminate because if the first infinity wins the tug of war, it'll pull the value of the difference towards infinity. If the second infinity wins the tug of war, it'll pull the overall value of the difference towards negative infinity. If there's a balancing point with relative growth rates, then we could get a constant out of this mess. Okay, so let's go ahead and apply some of our tools. What might we do? How are we going to make this an indeterminate quotient? Sophia?
Can you get a common denominator?
Yeah, let's go for a common denominator. I'm down. And so I'll go ahead and multiply that first fraction by x minus 1 over x minus 1. And I'll multiply that second fraction by ln of x over ln of x. And I'll write it as a single fraction now with the common denominator of x minus 1 times ln of x. Do we need to show that first step, x minus 1 over x minus 1 to the first fraction? Minus, and then the second fraction times ln x over ln x? We need to show that? You're okay? Go to the common denominator and write as a single fraction. Let's try again. As x goes to 1, x minus 1 goes to 0. minus the natural log of x, right? The natural log of x as x goes to 1, goes to 0, that does exist and equals 0, over 0 times 0. Is that indeterminate? Well, the bottom 0 times 0 is 0, so overall, there we go. Overall, I'm getting an indeterminate form. The denominator is not indeterminate. The denominator is going towards 0. So I generate a form that authorizes these Hopitals. Oh gosh. We've got a big mix, don't we? No problem. We're tough. This is BC. Big calculus. So here we go. The limit as x goes to 1 from the right. Derivative of the top, term by term. Derivative of x is 1 minus 0 minus derivative of x is 1 over x. So my top, the derivative, I'm just getting 1 minus 1 over x. Yes?
Yes.
Cool. The bottom, what rule must I use? X appears in multiple functions, have to use the product rule. The derivative of the first is 1 times the second, ln x, plus the first, quantity x minus 1, times the derivative of the second, 1 over x. This is going to give me an indeterminate form, again, unless I algebraically rewrite it. So I don't want to be stuck in the forever derivative cycle. I'm going to go ahead and make a common denominator on the bottom to simplify this fraction. So let's see if we can make this look a little bit prettier. On top, a common denominator would give me x minus 1 all over x. On bottom, a common denominator would give me x ln x plus x minus 1 all over x. So we've got a complex fraction here. Notice how the denominators of each of these is x. If I flip and multiply, that is multiply, right, by the reciprocal at the bottom, you see our x's are going to cancel out, and I'll get an actually simpler expression where I can try again. So on top of my overall, I just get x minus 1 after reducing the x's. On the bottom, I just get x ln x plus x minus 1. Can we try again? Uh-oh. Going good. Top's going to 0 over, bottom's going to 1 times 0 is 0 plus 1. Shoot! I'm going to use 0 0 again. Are you guys?
Yeah.
What are we going to do? Go to the hospital. You can try again. We have an indeterminate form, at least that authorizes these will be called, but there's good things, because what's going to happen to my numerator here when I differentiate?
1.
It's going to be 1. That's not part of either of my indeterminate forms, and so I see the end in sight, at least. The derivative of x minus 1 is 1 over, oh gosh, we've got product here. Derivative of the first times the second plus the first times the derivative of the second plus the derivative of x is 1 plus the derivative of negative 1 is 0. I'll do one rewrite because I've already extended the page till gray area is all over the slide. X times 1 over x is 1 plus 1. Look at that. Now, as x goes to 1, what happens to ln of x? Goes to 0. My top is 1, and my bottom is... Hey! So, is this ln of 2? No. Is it e to the 2? No. We just did a common denominator. We didn't do any natural log business or exponential undoing, and so my final answer is 1/2. That's pretty sweet. Awesome. Okay. So I had envisioned us doing one more, but I think I want to save that one. And let's close it up for the day. So saving the tangent, don't do the last one, okay? What does it mean to be an indeterminate form, to be ATE? What are indeterminate quotients, products, differences, powers? Try to do it from memory if you can. Which indeterminate forms authorize the use of L'Hopital's rule? And then how do we apply Hopital's rule? I think that does a good job of summarizing our main topics for the day. I'm going to pause the recording and then come back to you to share. Okay, ladies and gentlemen, let's go ahead and share then. What does it mean to be indeterminate? Right? What does it mean to be an indeterminate form? Riley?
That's when you can't determine what.
When you can't determine what the value of the limit is or isn't, simply by looking at it. I'm with you. I'm going to say can't tell what limit is or isn't, just by looking at it. There's more work to be done. What are our indeterminate quotients? Sydney?
Infinity over infinity, like plus or minus, like, and then the 0 over 0.
What's our indeterminate product? Grace?
0 times infinity.
Thank you. What's our indeterminate difference? Brendan?
Infinity minus infinity.
Thank you. And the big bad mother daddy of them all. Yes, that's right. What are our indeterminate powers? Kobe?
Infinity to 0, 1.
Plus 2.
Good job. Nice job. Which indeterminate forms authorize the use of Hopital's rule? Sophia?
Plus or minus infinity over infinity and 0 is 0.
Good. And how do you apply Hopital's rule? All right, what do you do to apply Hopital's rule? Marissa?
Take the derivative of the top and the derivative of the bottom separately.
Yes. So take derivative of the top and bottom separately, and then try again. I'm going to go ahead and underline my separately. And try again. Who's awesome? You guys are awesome. Great work today, and then you have a little bit of practice time. So go ahead and use this time now to work on your OTL, which is not on the printout, so you need to write it down. You'll notice that I put odds there, right? Odds there so you can check each of your answers, and I'm going to go ahead and save our recording.